Hi, in this video, I'm going to give you one example of one way or single factor ANOVA, okay? So here, the single factor stands for the variable. That single factor may have different columns, okay? More than one columns. That can be, that we denote, we say that is levels of the factor, okay? So before I start the example, what I want to do here is, let me tell you this note. Says that the sum of the square total, you see that we talk about mean square of the column, mean square of the error. There is one of the sum of the square. So mean square column was sum of square of the column, uses sum of square of the column, and mean square error uses sum of the square of the error. Similarly, there is one more type of sum we call sum of the square of the total. What does that mean? That means sum of the square of the deviations of all data from grand mean. That means you pick each of the data from all the samples and then subtract that from the grand mean and then square it and add that deviation. Okay, that is called sum of the square of the total. Sum of the squared total. Okay, and to find out the sum of the square of the error, there is another way to find out that, because for one way ANOVA, sum of the square of the total is equals to sum of the square of the column plus sum of the square of the error. That happens always, okay? Sum of the square of the total is sum of the square of the column plus sum of the square of the error. So thus, if you want to find out sum of square of error, SSE, if you don't want to use that S1 square, S2 square formula, the another way is you can do SSE equals to find out SST, find out this one, and then subtract the SSC from that. So you will get exactly the same value, okay? Let us jump to the example. So on this example, basically this example contains the data set that they feed 4 different types of diet for 4 different sample of pigs. Okay, so they were randomly picked. All those assumptions, we are assuming that those assumptions are not violated. This data set follow all those assumptions. Okay, so the data are normally, population are normally distributed, and the variance are equal, variance of the populations are equal. Also the data are taken from using simple random sampling and so on. Okay, now so this first set of pigs, first sample of pigs are feed diet 1, second sample of pig feed diet 2 and diet 3 and diet 4. There were total 19 pigs are assigned at random among 4 experimental groups. Each group is fed with different diet. The data with pig body weight in kilograms after being raised in these diets were presented below. So what they did is they measured the weight in kilograms after a certain time interval. Okay, they fed diet 1, diet 2, diet 3, diet 4 for different sample of pigs, and then they measured the weight after a certain time period. Okay, now what you want to see here is we want to test whether 4 different feeds result in different body weight in pigs or not. So we want to test whether all these diets have equal efficacy on the pig's weight growth, or they are, at least one of them are different. That's what we want to test. Okay, so here the body weight is depending on only one factor, that is the feed. Okay, so these are the body weight data, but these data are depending on these data are taken or measured depending on the diet. So these are the data for diet 1, these are the data for diet 2, diet 3 and diet 4. So basically you can say that the variable here is the diet, or the factor is the diet, and under the factor there are 4 different levels. Okay, so the factor is diet is the factor, right? And then I denoted by x1, x2, x3, x4. So these are the weights of the pig under each of these diets or under these diets. Okay, now So what is the null hypothesis here? I'm doing manually, and I will show you how to do R directly as well. Okay, so when I started to do manually, so the null hypothesis is mu1 equals to mu2 equals to mu3 equals to mu4, meaning the average weights of the pig under all these diets are equal to each other. Okay, that's what the null hypothesis is. And the alternative hypothesis here is the mean weights are not equal, meaning that not all of them are equal. Okay, some of them may be different from the other one. All right, now, so what we want to do, as I discussed in the steps, what you want to do here is first of all find out the x bar GM, meaning this is the mean of all these data sets. How do I find out? You add these plus these plus these plus these plus these plus, so you add 60.8 plus and then plus all together through 60.3 divide by how many data points are there? There are 19, because there are 5, 10 plus 4, 14 plus 9 is 19. So you find out that. If you find out that, you will get 67.8526. That's what you find out. Okay, so next what you want to do is you want to find out what is N1. N1 is 5, N2 is 5, N3 is also 4, and N4 is also 5. Okay, next what you want to do is you want to find out X1 bar. Let's find out X1 bar is the mean of the first column. Find out X2 bar, find out X3 bar, and find out X4 bar. Okay, that's what you find out. And finally you find out S1 square, the variance of the first column. Okay, find out the variance of the second column, S2 square, S3 square, S4 square. You find out all these values. Okay, look at this. This is what I found. N1, N2, N3, N4 are those. And then X1 bar, X2 bar, X3 bar, X4 bar are those. And then S1 square, S2 square, S3 square, S4 square are those. So what I'm doing here is I want to show you how I got these numbers in R. Okay, let us see that. So the very first I did X1, X2, X3, X4. That is the diet 1, diet 2. I copied that data. Okay, I copied those data there. Now, so what is K? K is the number of columns or number of samples. So K is the, here I wrote in a row form, but K is the number of columns or number of columns or groups, right? Or I would say columns. Okay, so here in our problem, number of columns are 1, 2, 3, 4 columns, or in other words 4 samples, or in other words 4 groups. Okay, now what is N1? N1 is the length of X1. How many data points are there? That is N1, N2, N3, N4, and uppercase N is the sum of all these, meaning uppercase N is the total number of data points. That is 19, right? So here it is N1 plus N2 plus N3 plus N4 will be N. That's what you get. Now, what we did is we found the mean of all these data points, putting all together. So what I'm going to do is I'm naming it as all data, and I'm collecting all them together. Okay, so if you do that, what do you get? You got all data is just putting all those data in a single group. Okay, all together. Why do you want to do that? I am just doing the finding the general mean, overall mean there. Okay, so finding the overall mean. So I denoted by X bar GM. So X bar GM is the grand mean of all those data points. So I did mean and then all data. So here to combine all them in a single data set, I wrote C and then X1, X2, X3, X4 separated by comma, right? And X bar GM is the mean of all these data set together. So I got X bar GM is 67.8526. You see that? that is the X bar GM, 67.8526. So the next thing you want to do is, so what is the mean of each of the, you can find out them separately, okay? So you can write x1 bar, x2 bar, x3 bar, x4 bar. But what I did here is I'm trying to find out the SSC directly. SSC is n1 times x1 bar minus x bar GMC, n1 times x1 bar minus x bar GM square, plus n2 times n plus n3. So I did all them together. But what we are using here is we are finding the column means, mean of that, mean of this, mean of this, mean of that. And then what you are doing is you are finding the difference of these means from the grand mean, and then square it and multiply that by n1. Okay, that's what it is happening. So let me write down that value there. I got 64.62. The another one is 71.3. Another one is 73.35. And the last one is 63.24. So what you are doing is you are doing n1 times 64.62 minus 67.85 square. N1 is 5 times, right? This is for the this minus that square, and then n1 times means 5 times, plus do the same thing, 71.3 minus 67.85 square times 5 times that, and similarly do for the other columns. Okay, this is what I am doing here, SSC. So the SSC is n1 times x1 bar minus x bar GM. x1 bar is basically the mean of x1, right? And then x bar GM is the mean of total, and square, and similarly do for the others and add them. You got SSC is 338.93. So 338.93, that's what I got this SSC. Now what is MSC though? MSC is SSC divided by K minus 1. See, MSC is SSC divided by K minus 1. I got MSC is 112.97. So 112.97. So what we got here is 111.4. So which is close. So what is happening here is the number of decimals you take. Okay, if you take more decimal, you will get more accurate. So basically R is taking more decimals, so we are okay. It is taking 4 decimal. I was considering here just 2 decimals. That's why I got a little bit bigger value there, but it's okay. Okay, all right. So that was the MSC. Now how do I find out the SSE? So to find out SSE, there are 2 ways. One way is, as I discussed here, you find out the SST and then subtract the SSC from SST. That is one way. Another way is just do n1 minus 1 times s1 square plus n2 minus 1 times s2 square, and so on. What is happening here is n1 minus 1 times variance of x1. So variance is s1 s square, right? So variance of x1 is so the s1 square, meaning the variance of the first data set x1. Similarly, variance n2 times 1 times variance of the second data set, and so on. So this is what I am doing. So SSE, I got 140.75. Okay, now if you use alternative method, what I did here is I'm finding SST. You don't have to do both, you can do one of those. So SST equals to sum of all data. What is all data? All data is all of them putting together, right? That's what all data is. That's what all data is. All data minus its mean. Mean of all data square. And then you add them. Okay? So find the mean of the square of the deviations of all the data from its grand mean, square it, and then add them. That is the sum of that. Okay? That is SST. SST. Now what will be the SSE then? I'm just giving another name, SSE1 there, okay, because there is SSE already. So that is SST minus SSC. So I got 140.75, exactly same as the other method I used. Okay, so you may want to use this one or that one, either method is okay. Now the next thing I want to find out is MSE, mean square error. What is the formula for MSE? MSE is basically SSE over n minus k. Okay, so SSE or SSE1, they're the same thing here. So MSE is SSE over n minus k, which I got 9.38. Let's see what I got here when I take the two decimals. 9.32 I got. Here I got 9.32. They are pretty close, right? Now, so that's how I find the test value or the F value. We also call test statistic. Now, so the next step here is you want to find out the critical value. How do I find out the critical value? To find out the critical value, we need to use alpha and the right tail test. Okay, so for the critical value, as I mentioned here, to find out the critical value, you use QF 1 minus alpha. Since alpha is 0.05, so QF 1 minus alpha is 95. K minus 1 is N1. This is the degrees of freedom of the numerator. And N minus K is the degrees of freedom of the denominator. If you do that, you get the critical value 3.28. That is the critical value. Let me see here. So degrees of freedom of the numerator is 3. That is K minus 1 is 4 minus 1 because there are 4 columns. And degrees of freedom of the denominator is total data points minus the number of groups. That is 19 minus 4 is 15. So degrees of freedom of the numerator is 3. Degrees of freedom of the denominator is 15. So this is how I find the critical value. Okay, this is the critical value by using R. But if you want to use table, so this is the F table for alpha equals to 0.05. Now degrees of freedom of the numerator is 3. This one is 3, right? And the degrees of freedom of the denominator is 15. So go to 3, 15. That is 3.29. You see that? 3.29. That is the 3.29 from the table. Okay. So look at this. What is your test value? So the F value here is 12.0404. Here I got F value is 11.97. They are very close, right? So F value is, the critical value is 12.04. Sorry, the test value is 12.04, not the critical value. Test value is 0.04 and the critical value is 3.28 or 29, right? Critical value is 3.29. So what is the rejection or acceptance criteria? Not reject or reject criterion. The method says that if the test value falls in the critical region, what was the test value? Test value is bigger, right? Test value is bigger than the critical value because the test value is 12 and then the critical value is 3. So basically the critical region is right side of the critical value is the critical region. So the test value falls in the critical region. That's why we reject the null hypothesis. That is the critical value method. But if you want to use the p-value method, so the formula says that to find out the p-value, what we use here is for p-value you use 1 minus pf critical the test value comma degrees of freedom of the numerator comma degrees of freedom of the denominator. So you do p-value is 1 minus pf, f value comma k minus 1 comma n minus k. Let us do that. I got p-value is 0.0003. So which is less than alpha, right? So p-value is less than alpha. So we reject the null hypothesis, right? Let me write down that. So p is less than alpha. So we reject 80. That means at least one of the at least one of the mean is different from the other mean in the population. Okay, so this is what I got. All right. So now how do I do this using R directly? Okay, you see that? So again, so how do I do this problem using R directly? So one of the things that you should be careful when you use R directly is you need to arrange the data in a specific way. Okay, what is that specific way? So you want to order, for example, this is what you want to do if you are using R. Okay, what you should do here is you need to write like all this data in a single column, like 60.8, 67, and then for the second column 68.7, 67.7, and then continue that way. This is the first column, that is the peak weight W, right? And then on the second column, what you want to do is you want to write those diet type. Okay, for example, this one is X1, this one is also X1, this first type of diet, and continue that way. Similarly, after this is X2, right? So X2, and then so on. And similarly, after some time, you will get X3, and so on, and then X4, X4. So you should arrange the data into this format. Okay, to perform ANOVA. All right. So this is what I want to do first, and then I will use the ANOVA built-in function here. See what is I'm doing here is P diet equals to C. I'm repeating diet 1. How many times I'm repeating? As many as how many data are there in X1. Okay. Similarly, repeat diet 2. How many times? As many as the number of data points in the second column, and so on. Okay. So this is what I'm doing here. If I do that, this is you get. See, first data, second, third, fourth, fifth data. 5 data are from diet 1, and other 5 data are from diet 2, and so on. Next, what I'm doing here is I am writing all these data into one row or one column. Okay, so that is the peak weight. It's C, X1, X2, X3, X4, which is same as the all data in the when you do it manually. So if I do this, this is what I got. Now I want to put them into the 2 columns. Look at that. That is interesting one. Look at this. See, the first, second, third, fourth, fifth weights are fed diet 1. And then 6, 7, 8, 9, 10th were diet 2, and so on. So you need to arrange the data in this format first. Okay, guys. Now, what you need to do next, what you want to see next is I want to see the box plot and then see are those average in each data set or in each diet are equal, or how does it look like in the box plot? I wrote box plot, peak weight, and then that wiggle thing, right? And peak diet. So what it does is it will create a box plot of these peak weights for each diet type. Okay, for example, so you will see the box plot of for 5 data, that is for diet 1. You will see the box plot for second 5 data or 6th through 10th data, and then you will see a box plot that is for diet 2, and so on. Let us see that. So this is what I got. Okay, so peak weight and then diet, peak diet, right? So diet 1, this is the median value. Okay, and this is the minimum value, maximum value, Q1, the first quartile, Q3, the third quartile, and this is for diet 2, diet 3, and diet 4. This is what you got. It sounds like diet 2 and diet 3 have the almost equal median, right? And diet 1 and diet 4 have the equal median. You can think that way, but since we are assuming that the data are normally distributed, then the mean and median must be the equal, right? Almost equal. You see that? So it sounds like the peaks weight of different diet are different. The average peak weights for different diets are different because they have the different box plot here. Okay, now, so this is just a visual, right? But you want to test, you want to do the analysis of variance. To do this, you see that result 1 equals to AOV, analysis of variance, peak weight, and then wiggle peak diet. If you do this, and then if you want to see the result, so I denoted this by result 1, okay, and the summary of the result will give you all those values. You see that? What did we get? Let me compare this result values. Let us compare what we got manually and then what we got from R. Okay, so degrees of freedom of the numerator is 3, degrees of freedom of the denominator is 15. Okay, sum of the square. What did we got on the sum of the square? So actually I erased, I think I did not recorded the sum of the square here, but I think I did SSE, SST, all those things here. So you got 338.9 is the sum of the square, and of the column, sum of the square of the error is 140.8. Similarly, mean square is sum of the square divided by the degrees of freedom, right? Divided by k minus 1 and n minus k. For this, you got mean square of the column is 112.98, which we have 111.47. Again, this is just the rounding error, okay? And then the mean square error is, we got 9.38 here, and here it is 9.32. So what is the F value? F value I got 12.04, and then here F value is 11.95. So again they are same. So actually what we got exactly same as we got when we did manually using R, right? So that is the F value 12.04. And what is the P value? P value is 0.0003 or 0.0028. This is what we got, 0.0029. So which is almost the equal, okay? So what can we say? We can say that we reject the null hypothesis, right? So null hypothesis is rejected. That means the average weight of the peaks with different diets are not same. Let me read a note there. There are different F tables for different values of alpha. This F table is only for alpha equals 0.05. Okay. And next is, since the test statistic F falls in the critical region, we reject H0. So we can say that there are not enough evidence that these 4 different diets have the same effect in the peaks weight gain. And another note is, if there are only 2 samples, k equals to 2, you can use t-test or ANOVA. Both will produce the same results. But if you are testing the difference between mean as a constant number other than 0, then the t-test is applicable. You know, sometimes you can say that in the 2 sample t-test, you say the difference between the mean is equal, or difference between the mean is, if you are doing the difference between the mean is equals to a constant number, then the t-test is used, not the ANOVA in case of the 2 sample test. Okay guys?